Been a great series so far. Thank you, Anna. And then Brennan will start on Thursday. Okay. Go ahead, Anna.
All right. So again, I'm going to share screen like last time. If there's any problem, just unmute and let me know. Hopefully everyone can see my screen right now. Okay.
Yeah, we got it.
Cool. All right. So just to have like a recap of what we have been doing. So we are focusing on something called like the Loehr-Warrington conjecture and how our group prove it. So like today I want to just start with the recap and like, okay, well, what is going on with all these like methods and what do we know, and like, and afterwards I'm going to talk a little bit about like all the terms that I touched it with some examples. Okay, so if you remember like the very first talk I talked about, or the second talk, I talked about like the relationship between the elliptical algebra element and also the symmetric functions elements, and then some cats related inside. So so that's kind of like the basic of like how we come up with all these proofs. So let me just really quickly just go through what is going on. So we have some elliptical algebra element. Okay, so these elements is associated to some symmetric functions. Okay, but so what it is like sometimes we see something like f of minus m x m n. Okay, so this m here is just some constant. Okay, so these mn's here, these mn's, whoops, too big. Let's see. So these mn's here are just, as I said, you just choose your favorite universe. They are like any integers relatively prime, and for each of them, for each pair mn, they give you a slope. So this slope represents a line, and that line gives you a universe, and you're just living in that universe. For each universe, they are just a copy of the symmetric function world. And then from this symmetric function world, choose your favorite symmetric function, say f here, and then you can create an elliptical algebra element. Okay, so it has an action on the symmetric function side, and if you add on the simple symmetric function 1, it actually would be the same as omega on the polynomial part of some cats. Okay. Okay, so that is the idea. So for each f, you can find some cat associated to it, and then you take the polynomial part of the cat. The cat is a series. It's like is a QT series. And then you take the polynomial part to make sure that is like you can write it in terms of like shear function, say, and then now you take the omega of it. Then that would be what it is when you have this symmetric, the elliptical algebra element adding on 1. So now, like our focus is that we want to know the mn version of the Loehr-Warrington, meaning that we are just trying to pick our symmetric function f to be the s lambda. So so what we have is actually we have this symmetric function s, and then we know that when we add on 1, okay, so that would give me something like a special cat called the Schur cat. Okay. Okay, so that's known. That's known. That is something, the relationship between the elliptical algebra side and also like our cat and animal side. Okay, so now so we want to know like, okay, well, what is the Loehr-Warrington conjecture? Loehr-Warrington conjecture says that I want to know a combinatorial interpretation on Nabra on S lambda, right? Or more generally, I want to know Nabra M on S lambda. So can you give me a combinatorial interpretation of it? And So like, how is it going to relate it to these guys? Well, if you set n equals to 1, that gives you the nabla to the power m as lambda. So I just need to know the combinatorial sign on these guys, and then just set n equals to 1 as a special case, and I'm all set. So this is the idea of the whole proof. So the whole paper that we have, we are mainly trying to construct a combinatorial interpretation on the polynomial part of the surecat. So that's that. Okay. So now, what is a surecat? How do you construct a surecat? So a surecat. So if you want to construct it, whoops. Okay. So surecat can be constructed by something called the Loehr Warrington dense and nest. So this is like in our second lecture that I give you some examples on how to construct a Loehr Warrington dense and nest, and they are the simplified version of the more general version of the dense and nest. Okay, and so now, what is our main theorem? Our main theorem actually is more general, saying that actually any cat constructed by dense and nest, you don't need to be Loehr Warrington style, just dense and nest, okay, has a LLT series expansion. So it's LLT series positive, okay, or not positive with a global sign. So at least we know, okay, any cat constructed by something called dense and nest, we all know that's our LLT series expansion. Okay, so as I said, like cats are series, right? So you take the polynomial part of this, so you get like the polynomial part of a cat. Okay, and then you of course take a polynomial part of this, then that gives you the LLT polynomial. Right, so that's great because now that just means that any cat constructed by dense and nest as polynomial part x of cat has a LLT polynomial expansion. Okay, so this is our main theorem of the whole paper. And then so now Loehr Warrington is just a special case of these cats because they are created by some dense and nest. So that is like the whole proof. So if we can describe what these are, then we are all set. Okay, so that's the general idea. Now I have been talking about lots of like, well, cats, right? And then to construct a cat, you have to have several things. So when we write a cat, we have this definition. So H of RQ, RT, RQT, and then you have your favorite lambda, and then you have like a big omega in SL. So you choose your favorite L. Okay, so choose your L, and then what are these RQ, RT, and RQT? They are just subsets of the positive roots. Okay, so positive roots are just the epsilon alpha ij that I usually use. So to recall what they are, so these are just epsilon I minus epsilon j, where 1 is less than I, less than j, less than equal to L. So that just means that like you have a 1 in the I position minus 1 in the j position. So the 1 is always on the left side of the minus 1 when you have a vector of L 1 minus 1 0. So L positions. Okay. So something like this. Okay. So in this case, if this, then this part L is 1, 2, 3, 4, 5, 6, 7, 8. So L is 10, and this is our alpha 3, 4, 5, 6, 7. So this is our alpha 3, 7. Okay, so that's what it is. So you choose something and lambda is here, okay? And then the whole part is kind of complicated. It's like x to the lambda, meaning the x1 to the power lambda 1, x to the power lambda 2, and so on and so forth. And then we have your alpha in RQT, and then so QT x, let me use this, ij, alpha ij in RQT, xi over xj. And then we have 1 less than I less than j less than L, 1 minus xj over xi, and then alpha ij in RQ. So that's the Q1, and then alpha ij in RT, 1 minus t xi over xj. Okay. So that's the cat. So this is our cat here. Okay, so now let me start with some examples. Like, okay, well, what are all these cats? Why do we have these things? And you may be like finding it weird that we have this xj, xi like this, while other things are xi, xj, and what is going on, right? So, so let's start with an example. And so first of all, I want you to recall something called a Loehr symmetrization. So, so we talked about this last year. Operator for GLL. Okay, so what it is that you give me any function f, symmetric function f, okay, f of x1 up to xl. Okay, so you add on this. So the definition is just this: omega w in SL, and then w, you put your f here, and then divided by 1 less than I less than j less than or equal to L, 1 minus xj over xi. Okay. Okay, so that's the Loehr symmetrization operator. And what do we know about this? Well, the Loehr character formula says that if you actually, I mean, this is any function. You can use it on any function. You don't need to have a symmetric function. So if you have f, if you choose this f as, so Loehr character formula. Okay, choose this f as like x to like a monomial x lambda, where lambda is the dominant weight, meaning that like lambda 1 is bigger than or equal lambda 2, and so on. We allow negative here. Okay, so that's the Loehr character formula. So that means you just need to choose your f as a monomial with a power which is like a dominant order, then you get like the irreducible character like this. So for example, if I want to create the Schur function, say 532, okay? So that is the same as chi 5v2 because everything is positive here, okay? And then so by this formula, that just means that is sigma of x1 to the 5, x2 to the 3, and x3 squared, okay? So what does that mean? That means you can just plug it in. So we have 3, L is 3 here, okay? We use 3 variables, so S3, and then W on x1 squared, x2 5, 3, x3 squared, divided by, actually I can just write out, 1 minus x2 over x1, 1 minus x3 over x1, 1 minus x3 over x2. Okay, because j is bigger than I. Okay, and so you may ask, okay, how am I going to write this out, right? So this guy, if you do some math, okay, so that is x1 squared x2 times x1 5 x2 cube x3 squared over x1 minus x2, x1 minus x3, x2 minus x3. Okay. And then you just symmetrize everything. Okay, so symmetrize everything, meaning that like you just, for example, if this W is just identity, then you get this whole thing. Okay, and then this whole thing. Okay, and then if this W is like say S1, meaning that you swap 1 and 2, then you will get, because this guy here is x1 7, x2 4, x3 squared. So now if you swap 1 and 2 and see what happened. So if this is S1, then we'll get x1 4, x2 7, x3 squared divided by x2 minus x1, x2 minus x3, x1 minus x3, right? So, and then you just run all these W in all the 6 permutations that we have and then add them up. And notice that the denominator is always the same, just changed by a sign. So that the sign is actually the length of your permutation. And then, and then you add everything up. And that numerator will be divisible by this product. And then you will get a very nice expression. And that expression is your shear function. So, okay, so why do I talk about this? So go back to the Weyl symmetrization operator here. So see this guy, if I just use this, okay, as our x lambda, right? So it's like our case x lambda, then this is our x lambda. So this is very similar to our cat, right? Because our cat has this x to the power lambda part. We have this like xj over xi part, but we don't have the rq, rt, and rqt. So basically this guy is just h. You don't have q reset. You don't have t reset. You don't have qt reset. And you just pick your lambda, okay? So you can see like our cat is just like a more generalized version of this Weyl symmetrization operator. So what it means is that if you want to find your irreducible character here, x lambda, or your shear functions s lambda, you just basically have this cat. You choose you don't have any q root, t root, or qt root, just choose your lambda and you are all set. So that is one example. Now let me give you another example. So the next example that I want to give you is the Hall-Littlewood symmetrization formula. So how do we create Hall-Littlewood with the cat? Okay. So here it is. So that's the Hall-Littlewood symmetrization. I don't hear anybody complaining about my screen, so I'm assuming that everything was great. All right.
Anna,
So,
can you lift up the screen a little bit?
Yeah, sure.
Yeah. Now what this reminds me is this sum that you have symmetrization, and especially with the numerator polynomial, and the fact that you have the successive differences there. It reminds me of Postnikov's work on volumes of permutohedron geometry. So maybe you can think about something like that.
Oh yeah, that's a good point. Yeah, thank you.
Yeah.
All right, so let's look at Hollow-double symmetrization. So that is like, remember, we are saying that, okay, well, if you have a symmetric function over Q, the rational field, then we have the sure function, right? And then if we change our field to QT or QQ, depends on what parameter you want, then you get a Hollow-double. If you add another parameter like QT, then you get the Madonna polynomial. So I want to show you like, okay, well, what is the Hollow-double symmetrization in our case here? Okay, so so if first of all, I'm going to give you a Loehr polynomial. Oops, cannot spell. Okay, over the field, any field containing QQ. Okay, so Loehr polynomial meaning that you can accept negative powers. Okay. So this is our operator. So this is called the so this guy here. I'm not sure if you see the color, maybe not. This guy here is very similar to our sigma in the previous case, but of course now we have a larger field, so I have to use another operator. So this is going to be an upgrade of the original. So how do we define this guy? So this guy, if you put any Loehr polynomial, then it is defined as sigma of this. Okay, so pi I less than j, so 1 to L, 1 minus Q. This time I have xi over xj. Okay. So again, this is very, very similar to our previous case. Our previous case did not have this part. Okay, so this is an upgrade. So but it is very similar, right? Like you can see that we still have the whole kind of like a whole positive reset here, just that we have this Q power here, and then we have xi over xj. So this is like how we set up this. Okay. If there are too many notations here, I can just write out. So it's like any W and SL. And then now you have this W adding on I1 less than I less than J less than L, 1 minus xj over xi. This part is because of the sigma. And you also have 1 less than I less than J less than L, 1 over Q xi over xj. Okay. So this is like an upgrade of our sigma. Now, how do you create a Hall-Littlewood polynomial? So again, there are many versions of the Hall-Littlewood polynomial. This one is the dual case that I'm going to talk about. So, so here, as before, if you choose it to be x to some power, let me use mu so that like I can say it in a better way later. So if you choose x mu, unfortunately, this time you're going to get a series. And you will see what I mean. I'm going to give you like an example, and then you will see why I have to take a polynomial part. So I'm going to take something called polynomial part, okay, of that. And this guy is going to be your dual Hall-Littlewood polynomial. So this is the, this you can write as lambda k lambda mu q as lambda. So this guy is the k, the q Costa coefficient. Okay. So, but anyway, so like all these terms are not super important in this lecture. What I want you to know is that you can actually create the dual Hall-Littlewood polynomial using this upgrade of the sigma, which we used it to create a sure function. So we have this upgrade, but this upgrade is actually more general, that you get a series instead of a polynomial. So you have to truncate it, and then you get your dual Hollow-dual polynomial, which you have a nice expression in terms of the shear functions, which the coefficients are all the Q-Cosca coefficients. So let's start with an example. I'm trying to make it like easy. I think these are the examples that I talked about last year as well. So, okay, so let's create this. I use maybe 5, 3. I think that's what I used last time. So this guy, all right. So what does that mean? That's x1 to the power 5, x2 to the power 3. And so we only have 2, like the SL, the L is 2 in this case, okay? So our W is just in S2, which makes our life should be much easier. We only have 2 things to deal with. So x1 to the power 5, x2 cube, and then we have 1 minus x. So remember this guy, so let me just put it here, okay? So here, because it's 1 and 2, right? So my I has only one choice, which is 1. My J has only one choice, which is 2. So that's great. So the first product here is just one term, x2 over x1. The second term is only, again, one term, is just x1 over x2. Okay, so that's that. All right. And then, so now let's really compare it and see what that is. Okay, so this one, if my W is identity, then I get the whole thing, right? Oops. Duplicate. If W is just S1, then we have that. So we have this guy. But what does that mean by S1 adding on it? So S1 adding on it, meaning that we are going to swap X1 and X2. So let's do it. Let me just do it in another step. So this is just 3 and 5, okay? And then now we have X1 over X2. And then we have X2 over X1. Okay, makes sense. All right, so how do we, oh, I know, so we have to remove that. Now, how are we going to compute this thing? So there's some skill here. So the first thing is that we would treat anything with a Q here as the way that you do this. Like, remember when we were in like learning calculus, maybe this guy, let me use y equals 1 plus y squared plus y cubed plus da, 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 right? So we are going to treat these two with the q here as this, okay? We're going to use that. But these two guys, we're going to keep. So anything here, which is coming from the positive reset, we are going to keep it. And then if you are having some coefficient like a Q or QT or a T, then we are going to deal with it with this case. Okay, so let's really do it and see what I mean here. So the first one here is like x1 5 x2 cube. And then multiply by x1 minus x2. So all these guys are from this side. Okay, so from this side, so it's this. And then now I'm going to multiply this here. 1 plus q x1 over x2 plus q square x1 square over x2 square q3 x1 cube over x2 cube, dot, 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 dot. Okay, I hope that is clear. All right, and then we do the other thing. So the other fraction, let me do it in the other row. So same idea, we have x2 times x1 cube, x2 to the power 5, but this time it's x2 minus x1. And then now I have 1 plus q, x2 over x1 plus q square, x2 square over x1 square, q cube, x2 cube over x1 cube plus dot, 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 dot. All right. So again, stop me if you cannot follow what I'm talking about. All right, so let's simplify this. All right, so so every term here, so let's see. So this guy is just x1 6 x2 cube, right? This guy is just x1 cube x2 6. So both of them has x1 cube x2 cube, so we can take it out. And then both of them has the denominator x1 minus x2, just different by sign. So we can take all these out. Okay, so take it out. x1 cube x2 cube over x1 minus x2. All right, so what do I leave there? Okay, so this guy has x1 cube times that whole chunk. Okay, so I duplicate and put it here. All right, and the other one is just x2 cube. And you can see that it's just the same thing, but I have a minus sign here, I think. Minus sign because that was x2 minus x1, but I take out x1 over x1 minus x2. And then now I have the same thing here. All right, so now how do we compute that? So that's x1 cube, x2 cube, x1 minus x2. Now to compute it is actually quite fun. At least for me, I feel it's fun. So like each of them is multiplied by 1, right? So we do x1 minus x1 cube minus x2 cube and group them together. Okay, so x1 cube minus x2 cube, group them together. The cube power, we have x1 4 over x2 minus x2 4 over x1. Okay, q square, we have x1 fifth over x2 square minus x2 fifth over x1 square. And one more term, okay, x1 6 over x2 cube minus x2 6 over x1 cube and dot, 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 dot. Okay. And then you can see that each term is divisible by x1 minus x2 in some sense. Okay, so what do I mean here? So the first term, of course, is divisible by x1 cube minus x2 cube. So you have x1 cube, x2 cube times the first guy is x1 squared plus x1, x2 plus x2 squared. Right? And then the next one is, so what is this, right? So this one is x1 fifth minus x2 fifth over x1, x2. So you can cancel them very nicely. So this time I have x1 square, x2 square times x1 4, x2 cube, x1 cube, x2, x1 square, x2 square, x1, x2 cube plus x2 4, right? And then the next one, so that's with the q. And then the next one is q square, x1, x2, x1 to the power 6. So why is that? I just take it slowly. x1 7, x2 7 over x1 square, x2 square, right? So this 3 to the square, then you have x1, x2, x1 7 minus x2 7 divided by x1, x2, you get x1 to the power 6, x1 5, x2 up to x2 6, right? And then, and so on and so forth, okay? And then if you do some, like if you do all these calculations, some of them, you can see that like eventually your denominator will have power bigger than cube and cube, so you will have some denominator. So say for example, if you, so you should be able to guess the pattern. This one is just xq cube and then x1 7 and then up to x2 7, okay? And then q to the power 4 would be x1 8 up to x2 8. But this time you're divided by x1, x2, right? And then q to the power 5 would be 9. Is it 9? Sorry. I think this one is actually more. 7 and then would be 9. Let me just check. Q to the power 4 is actually 10 and 10. And then this one would be 12 here. Okay. That's the.
And you want 8 after the Q cubed?
Yeah, 8, sorry. Thank you.
Huh.
Yeah. Yeah, because it's add 2 for each of them. Thank you so much. So then this is like x1 square over x2 square and so on. Okay. So now how do we write in terms of like chi, right? Like the irreducible characters. So this guy is actually the chi 5, 3. And you may ask like why, right? Like, and how do we get this guy? This guy, remember, is the one that we have the ones. We never touch the Q. So it's just the same as like, we don't have the Q at all, right? So what is this? This is the Weil symmetrization formula, which we already knew the result, which is the S lambda. So this is like, this is why you can easily see that that's the chi 5, 3. Okay. And then, or the sure 5, 3. Okay. So actually, if you write everything out, that's S 5, 3 plus Q. And this guy is just S, I think it's 6. So you just look at the power, the highest power here. So that's 6, 2. Okay. Q squared S 7, 1. And then plus Q S 8. And then Q cube S 8. And then Q4 is not sure function because sure functions with a negative number doesn't make any sense when we're talking about partition as a index. So that becomes our chi. Okay, so that is the 9 minus 1. Q5 chi 10 minus 2. Q6 chi 11 minus 3 and so on and so forth. Okay, so what is this? What did we calculate? We calculate this guy. Okay, so that's the whole symmetrization on x15 and x2 cube. And you get this guy. So you can see that it's a series already, right? It's not going to end. You can have more powers, more chi. And now if I truncate it, okay, so what we mean by truncating it is that you first of all write things in the chi lambda, okay? And then we only take the part which has the sure function part, meaning that we only want these parts, okay? So, so we have S5, 3, Q S6, 2, Q square S7, 1, Q cube S8. So this is a dual polynomial, okay? And all these are just, including the 1, they are all the Q-Koska coefficients. So that is what I mean by taking the polynomial part. It's just not like you expand it and just take the part which with positive powers of the xi's. It's not. You are actually writing them in terms of irreducible characters and including the virtual one, meaning that you have a minus sign in some of your indexes, and you take the positive one so that you can write in terms of sure functions to make sure that it's just a symmetric function in the ring. Okay, so I hope that makes sense to you. All right. So now, okay, go back to our cat. So we said that like if we have the original Weil character, like the Weil symmetrization operator, right? Here, this guy here. It is just our cat when choosing our root set, like QT and QT are all empty, and then you just pick our favorite lambda, weekly decreasing. So now, how about our upgraded version, right? So let's look at it. Our upgraded version here includes this, right? Which is our Q root set. And what are the roots that we pick? We pick every root. So that just means the whole symmetrization, we have this x mu. So x mu is actually our cat, but we pick our Q root set as the full root set. We don't have T reset. We don't have QT reset. We have our free fit mu here. So that's our cat. Our cat actually, again, generalized the Hall little width by choosing this. And then if you want to get the dual Hall little width, what you need to do is just to take the polynomial part of our Hall Littlewood cat here, right? So you can see that like changing your choice of your the resets give you different things. And that's why there are lots of freedoms there that you can create your own cat and maybe they represent something. In our newest paper that we will I think we will post on the archive very soon is that we actually modify the cat and then also give you something called a mechanimal. So we can talk about Madonna polynomials using the modified cat. And then we also have so that gives us a raising operator style thing. So it's just like, okay, well, because all these cats tells you how to create a series. So we can actually also write the Madonna polynomial in a certain way like this. And then because of the MN, the choice of your universe that you like, we also have an MN mechanimal in that case. So that is something that like you can see that you can have a lot of like freedom on your cat and you can modify something and then create something that you may be interested. Right?
Anna?
Mm-hmm.
Once you, when you truncate, then you write a Q expansion coefficients being sure function polynomials. Now, is it possible to predict which sure functions appear or which lambda appears?
Oh, you mean like which lambda that appears here?
Yeah, like
guys?
5362, blah blah.
In this case, yes, because you can see the pattern very quickly. But in general, no. In general, we don't know how to write the expansion of our like cats into our sure functions most of the time. In this case, we do, but most of the time we don't.
Okay, thank you.
Sure. All right. So now, so hopefully now you have a better sense of what is like a cat. So like what we do here is that like you can start adding up more polynomials in the denominator, and then you can just take not the full reset and then just create your own cat and see what it is. And then maybe some of them are like sure positive, some of them may not be sure positive. Do they have a global sign? And maybe they have a mixed sign. It really depends on the choice of your RQ, RT, RQT, and also your lambda that actually just like contribute a lot. And in our other paper, we have an LLT cat. And so that's a generalization of our sure cat. But the LLT cat is more algebraic. We don't have like a very nice like big path style interpretation of all these cats yet. So maybe that's something that you can explore as well. So so I think for I'm going to talk a little bit more, but for now, any questions about all these terms? Is that clear? So just feel free to unmute yourself if you have any questions. Okay. All right. So the next thing that I want to introduce, like I've been talking about a lot of like den and nest, right? So what are they? And I told you the version of den and nest in the most kind of like the easiest case, which is the Loehr Warrington case. But I want to show you the one that we actually use for in general. Okay. So let's start with a definition. So then is a tuple with 4 things, H, P, D, and E, where we have some criteria. Our H has to be a positive integer. And then our P has to be a irrational number. And then our D is a vector starting from D0. Okay. The reason that we start with 0 is because we are going to plot it on the y-axis. So the x-coordinate is actually the 0. But so that's why. And dh, so it is a vector with h plus 1 entries, and the h has to be positive integers to make this make sense. So you have at least one entry here. You don't have an empty thing. E is again starting with 0, and then move on to each. Okay. And then all these guys has to be integers. So this is like integer sequence. Okay. And then they satisfy this di minus dj plus 1 divided by j minus 1 is bigger than p. For 0 I minus j less than h minus 1. I minus ej minus 1 over, oh sorry, j minus I. J minus I is less than p for all 1 less than I less than j less than h. Okay, so you can see that E is like shifted 1 on the right, and then D is the one kind of shifted left. So start with 0 and then h minus 1, and then E is like from 1 to each there. Okay, and then also we have to satisfy more conditions. D0 it has to be bigger than E0, DH is less than EH, and also we want DI equals. All right, so all this condition is going to help us to be able to draw all these nests, and then we have like a very nice, the P is actually a slope to kind of like helping us to draw the path. So you already have seen it in the Warrington version, but that is the definition. Okay, so that is it then. So you can choose your favorite H, your favorite P, and then find the D and the E satisfying all these conditions. It's not easy, okay? It's not easy to construct a den, but if you satisfy this, that creates a den, and the den is very important because with all these constraints, that's helping us to create our resets. So all these D and E are going to help us to decide what is the Q, our Q, like the Q reset that we want, T reset that we want, QT reset that we want, and also the integer sequence that we want to create our cat. Okay, and then so that's the reason why we have all these constraints, because you will not just randomly create a cat here, because if you create a cat using all this data, then you will create a cat that has a combinatorial interpretation, which is a big thing, right? So that's why we have all these constraints here. Okay, so that's the thing, right? And then we have all these like so we have some terms, not too important, but because for completeness, I'm going to tell you these are all kind of related to animals. So IDI, so the DI is on x equals I. So the DI is the y coordinates of the point that you're going to plot on the x equals I line. And then those things are called the heads, okay? And then for the E's are called the feet. Okay. And then for the IJ, such that EI is less than J less than DI, they are all called the sources. Okay. IJ such that DI is less than J less than EI are called the sinks. So what is going on here? I usually just remember it like this. So you have a straight line on the x equals to I thing, okay? And then you have all these points that you plot according to your D that you're choosing here. And then so the top guy here is the head. Okay. This guy is the foot. So this is the case if DI is bigger than EI. So if your head is above your feet, okay, so then all these guys are called a source. Okay. And then if your cat is just flipping around with that foot is here, head is there. Too bad because of my move, I don't have time to draw animation. Otherwise, I would definitely have drawn this. This is like the head, okay? And this is the foot. And then, so in this case, that just means that if DI less than EI, okay, then again, from the foot, like from the top guy to the guy above the head here, they're called the sinks, okay? But you also have like a situation when your head and the foot are actually the same, so DI equals EI, then we don't give you the name because you already have two names. Okay. So that's like what we call sources and sink. If you compare it to our video last week talking about the Loehr Warrington source and the sink, you realize that in our Loehr Warrington part, we only have one source and one sink, right? And but actually in general, you can create more sources and sink depending on what your DI and EIs are, right? And then like the main theorem that we talked about last time includes some G. So what are the G's here? So the G is going to help us to know what are the like the root set that you're going to pick. Okay. So where GK I equals to 0, K minus 1, DI minus EI. Okay. Okay, so that's that. All right. So and then how do we interpret these guys, right? Like say this guy here. Okay, so these guys actually what it means is this. So let me just do this. So graphically speaking, what it means is like, okay, if you have both heads, because these are heads. Okay, so you give me two heads here, P, okay, and then a Q here. Okay, so both heads. Okay, and then you draw a slope P line. So before that, I should say this. So any two has P and Q. The P is on the left, okay? And you look at the point here, which is like P plus 0, 1. So you just shift it up, the lattice point just above P. And then any line with slope P has to be above Q. So any line that you draw in between here, slope minus P, sorry, slope minus P has to be like above Q. Okay, so that is what it means by that. Okay. So you can do a similar interpretation for the E. So let me just tell you what that is. For the E part, let me just go back, oops, and do this. So what does that mean here? Oh, I can actually just show it here. What it means is that if you give me both feet, P and Q, but P prime, Q prime, okay? So both feet. Then do the same thing, but flip it. So you look at the point here, Q prime for 0, 1, okay? So any line passing this segment with slope minus P has to be above P prime on your left for any P prime, so any pair. So these are the conditions that they have to satisfy. So that's how you create your thens, all right? Any questions? So I hope that that makes it like easy. And then, okay, so what are all these conditions talking about? Well, this is going to tell you that there is at least one source, right? Because you have a head bigger than the foot, so there is at least one source because like the head is a source. And this is just telling you that you have at least one sink. Okay. And this is just telling you that the number of sources has to be the same as the number of sinks. Why is that? Because remember, we have all these nests. The nest is just connecting your source and the sinks together. And we want to have each of the dig path, which is connecting your source and connecting your sink. And then so you get a nested dig path. And then the nest is the same. It's just the east end path satisfying all the conditions that I talk about in the second lecture. So I'm not going to repeat that because today's lecture, I just want to kind of like clarify all the details that we talked about in the last two lectures. So like now I tell you a more generalized version of the den and the nest of the den, and then you can create your nest there. And then, yeah, you can use that to create your cat. So I know that I only have 4 minutes left. So instead of doing this, I am going to go back and then give you something to look at. So let's look at the main theorem. Okay, so that's the main theorem that we talked about last time. Okay. And all these you can find it online on my website, and I'm going to give all of you links to access all these notes. So you can, what I want to mention is that, okay, well, any den that we construct like this, and then we have the G that we talked about just now, and then they help us to talk about like, okay, what are the Q and T? So these G's are telling you what are the squares that you take away from the positive roots. So for example, if your G is 1, 2, 3, say, I mean, it doesn't make sense, but I mean, like, okay, so say, for example, we usually draw roots like this. And so like, so why do we draw root like this? Because this is like row 1, column 2, row 1, column 3, and so on. So you can see that this is actually alpha 1, 2, alpha 1, 3, alpha 1, 4 to make sure that the I is less than J. Okay, so that is all the positive root in that scale case on the right. And then so how, say, for example, if my G is really 1, 2, 3, say, then what does that mean? So you draw a square 1, draw a square 2, draw a square 3 here, okay? And remember your whole root set, the positive root set is right here, bounded by the staircase. So now what is our RQ and RT? With all this G here, you just like get these above your square. Your square is the blocks that cuts the positive root set. So these are going to give you RQ and RT. So that's what here means. You can see this like G1, G2, G3 with these blocks. And then we are going to use these root sets as our RQ and RT, okay? And then what is our RQT? After you do this, you have all these squares, right? So you have all these squares from the 1, 2, 3. And then now for each 2 square, you also remove all these, okay? So let me use another color to make it easier to understand. So we have this guy and this guy, and then these guys are kind of like created by these 2 squares. So we also take it out. And these 2 squares here is, we have this guy, right? We also take it out, and then we just have these. Then that's our RQT. Okay, so that's what this means here. Okay, so the G is helping us to choose our reset. And how is the then and the then helping us? The then is giving us all these data to help us to create our the sequence. So we have a way to create our resets and our sequence, then you create your cat. Now, the big thing here is that if you create a cat like this, you are guaranteed that they can be represented by an LRT series. And then when you take the polynomial part here, you're going to have a interpretation using the LRT polynomial and with all these nests as your combinatorial object to talk about all these statistics. So that's the big thing. And then now when you go back to the Loehr-Warrington conjecture, then we just need to make sure that like all these things are matching the Loehr-Warrington combinatorial interpretation, and that's that. So you can see that Loehr-Warrington, the S lambda case is actually a very specific case of this result, because this result is more general for any cat. So if you want to see more details, then you can look at the my notes here. So the way that we actually prove it is using a bunch of like non-symmetrical Littlewood polynomial and other things. So like Hacker algebra and non-symmetrical Littlewood E and F, and they also generalize like atoms and like keys and so on and so forth. So, but I'm not going to bore you with all the details. If you are interested, you can go to the website and see all the examples there, but hopefully now you have an idea of how I'll prove that. So I will end it here.
Yeah, that's great. Any questions for Anna?
Hey, guess I've got
Hi.
one. Great talks. You really did a good job selling these cattle animals. So so we have this kind of dichotomy, right? We have these tame cattle animals, and I guess do you call them wild if they're not tame?
We didn't have that yet. But
Okay,
yeah.
I guess I'll call them wild cattle animals. And the tame
Okay.
ones are coming from the shift in algebra action. The wild ones is a little bit less clear. Are there any wild cattle animals that have a nice combinatorial interpretation or nice connections to algebra or anything like this?
The short answer is we don't know, but we know that there are like tame cat and animal are not the only ones have good like results. We still have a lot of things that that we don't know, because like there are RQ, RT, and RQT. When you're tame, you have to satisfy all these like crazy relationships. But like we actually run some data and realize that sometimes if you pick a non-ideal reset, and then you still get actually the same tame one, even though they don't satisfy the tame condition. So yeah, so there are actually wild ones that may not be tame at all, but they have good combinatorial interpretation that we don't know. So there are a lot of things that you can explore there.
And so to be tame, your three sets have to be ideals at least.
Yes,
but
yes.
other stuff too that's complicated.
Oh yeah, the other stuff is super complicated.
And tame is like if and only if coming from the Schiffman action on symmetric functions. So that is kind of a okay. It's a one-to-one. Okay, thank you.
Sure.
Any other questions? No? Okay. Well, we'll see you all Thursday then.
Yep.
Come on.
Bye. Have a nice day.